Hello and welcome back. In today's video, we are going to discuss the case of step potential in quantum mechanics. Specifically, what happens when a particle approaches a step potential whose barrier is greater than the particle's energy. So you can imagine a ball with a certain amount of kinetic energy hitting a wall, but it doesn't have sufficient energy to overcome the barrier of the wall. What is going to happen? Well, the answer should be the ball will get reflected back. That is the classical understanding of what should happen. But in quantum mechanics, something very interesting happens. Even though the particle has an energy which is less than the barrier that it is facing, there is a probability that the particle can penetrate through the barrier. There is a probability that the particle can exist inside the barrier. This is what happens in quantum mechanics, which is extremely different from what we expect from classical mechanics. And this is what makes quantum mechanics so very interesting. Now, there are two cases to the step potential problem. One is the case where the particle's energy is greater than the potential barrier. That case I have discussed in my previous video in complete detail, where I have obtained the reflection and the transmission coefficients. So if you're interested in that case, you can check that previous video. In today's video, I'm going to solve the Schrodinger equations for a particle's energy less than the potential barrier of a step potential, and I will show you that there is a probability that the particle can be found inside this particular barrier. This kind of quantum tunneling or penetration has a lot of applications in technology, which I'm going to discuss in much detail in a later video. Right now, let me actually prove to you that this is going to happen. You see, in quantum mechanics, the fundamental equation is Schrodinger equation. So therefore, I'm going to solve the Schrodinger equation in region number 1 and region number 2. So in region number 1, if we look at the Schrodinger equation, minus h cross square 2m d2 psi 1 upon dx2 plus v psi 1 is equal to e psi 1, where in region 1 there is no potential. The particle is essentially a free particle before x is equal to 0, so this comes out to be 0. This equation simply ends up becoming d2 psi 1 upon dx2 plus 2m capital E upon h cross square. E being the energy, m mass, h cross is a Planck constant. Psi 1 is equal to 0. Alright, so here I can assume this as a constant, d2 psi 1 upon dx2 plus a constant k1 square, which is essentially the wave number associated with this incident particle's wave-like motion. So the incident particle can be thought of as a plane wave which is approaching this step potential barrier. And this plane wave has an equation which is a Schrodinger equation, that is this one. And it has a certain solution. If you look at differential equations like this, it has a standard solution, so which I'm going to write here so that I can just keep all the important stuff in the left hand side. It has a standard solution that looks something like this. Psi 1 is equal to a e to the power iota k1x plus b e to the power minus iota k1x. The solutions of this differential equation are oscillatory solutions. Now, because in quantum mechanics we look at plane wave solutions which are complex, therefore I have taken the most general expression of that particular solution. So this is a complex expression which is essentially an oscillatory solution, which are basically the combinations of sines and cosines. Now, what does these two terms represent? A e to the power iota k1x essentially represents a forward moving wave, okay, which we can call as incident wave. By wave, I mean the matter waves associated with the incident particles. And the second term, b e to the power minus iota kx, this is the reflected wave, okay, the wave that experiences reflection after striking this potential barrier. So that means not only there's a wave which is approaching this barrier, there is going to be a reflected wave also which is going backwards. Okay, you can imagine the motion of a particle approaching this kind of a barrier as a wave propagating and hitting that barrier. So the moment you think like that, the quantum mechanical behavior becomes apparently easy. You know, when a wave is approaching and hitting at a barrier, a certain amount of wave has a probability of going back. And that is the reflected wave. And the initial wave is the incident wave. But what is interesting is that the solution of the Schrodinger equation does not give us a vanishing solution in the region number 2. We have a non-vanishing solution here. So let us therefore write the Schrodinger equation for region number 2 as well. So if we write the Schrodinger equation for region number 2, it simply turns out to be minus h cross square upon 2m d2 psi 2 upon dx2 plus v psi 2 is equal to E psi 2. What is the potential in region number 2? It's V0. It's a constant potential of V0 that extends to infinity. Okay, this is not some finite width. It's extending to infinity, this constant V0. So if this is the case where V0 is greater than E, then I want to write it in this particular manner. d2 psi 2 upon dx2. This is equal to, this is V0 by the way, not 0. This is V0. Let's remove the negative sign here. Let's take it to the right hand side. And this should become minus 2m upon h cross square V0 minus E. I want to keep this term positive. Therefore, I have taken V0 minus E. Therefore, there is a negative sign that appears here. And psi 2 is equal to 0. If I say that this constant is K2 d2 psi 2 upon dx2 minus K2 square psi 2 is equal to 0. What is the solution of this kind of a standard differential equation as opposed to this where there is a plus sign involved? Now in quantum mechanics, we are mostly dealing with these kinds of differential equations. So it's always helpful if you are familiar with certain standard differential equations and their solutions. So differential equations of this form where there's a plus k1 square has oscillatory solutions like this. But differential equations of this form where there's a negative constant square has exponential solutions. Okay, so the solution for region number 2 can be written as psi 2x is equal to c e to the power, there is no iota here, it's simply k minus k2x plus d e to the power plus k2x. Okay, while this was an oscillatory solution in region 1, this is a combination of an exponential decay and an exponential increase in region number 2. That is a solution of the Schrodinger equation in region number 2. However, we know that whenever we have solutions of Schrodinger equation, it must make sense in the context of the system, and the wave function that we actually end up getting needs to satisfy certain properties. So for example, if we look at these two terms, the first term is an exponential decay term, right? If you look at the first term, it's an exponential decay term, like this, right? And if you look at the second term, it's an exponential increase term, right? So if I consider both these two terms in region number 2, the wave function is going to blow up if the second term exists. If the second term exists for x greater than 0, the wave function will suddenly blow up and it will approach to infinity. That is not allowed. We do not allow for wave functions to blow up because we won't be able to normalize it and it won't make any physical sense whatsoever. So therefore, the only way to save ourselves from this kind of a catastrophic scenario is that I assume that d here is simply equal to 0, this particular constant. That means the only remaining term that we have is psi 2x is equal to c e to the power minus k2x. That is the Schrodinger equation solution in region number 2 where the particle's energy is less than the potential barrier. So it is not exactly equal to 0, it is non-zero. Alright, which means that the particle has a probability of existing in region number 2. So if we calculate the probability density, what is the probability density? The probability density that the particle will be found in the region x greater than 0 is nothing but psi2 mod square, which is equal to c being a constant mod square e to the power minus 2 k2x. The probability density in region number 2 is c mod square e to the power minus k2x, k2 being this particular term, okay, where k2 is equal to root over 2m v0 minus e upon h cross square. So clearly, number one, the particle doesn't have zero probability in the region number 2. It has a non-zero probability of existing in region number 2, which is in sharp contrast to what we expect in classical mechanics. In classical mechanics, if a ball is approaching some kind of a wall with certain amount of energy, if the energy is not sufficient enough, it will simply bounce back and go back, right? But in the quantum mechanical case, if an electron is approaching a potential barrier, then even if the electron doesn't have sufficient energy, it has a certain likelihood of being found inside the barrier. It has a certain amount of likelihood of penetrating through the barrier. This is something very unique in quantum mechanics that is not allowed in classical physics at all. So this is the probability, which, by the way, decreases exponentially from x is equal to 0. So there's an exponential decrease in the probability. So as we go deep inside, the likelihood of the particle being found will be less, and even more less. So we can find out the values of all these constants and their relationships by applying boundary conditions. All right. So let us see what further information we can find out by applying boundary conditions. You see, whenever we have a particle in some kind of a quantum mechanical system, and we are interested in the wave function solutions in that particular system, we have certain kind of conditions that we need to maintain. One is that there is a certain continuity of the wave function, because we want the probability density of the particle to vary in a continuous manner. And the second is the continuity of the derivative of the wave function, because we want the momentum of the particle to vary in a continuous manner. Which means that here, at this particular sudden rise in the potential, of course, this is an ideal case scenario. In a realistic scenario, we won't be having this sudden jump in the potential based on the application of a sharp force. So we might have a certain steep gradient of an increase in the potential, right? But to make our lives easier with the mathematics, we have this kind of a ideal scenario with a sharp jump in the potential. Whatever it is, at this particular x is equal to 0 barrier, when the particle interacts with the potential, I want to impose that the wave function in region number 1, psi1 at x is equal to 0 is equal to psi2 at x is equal to 0. By the way, these are the solutions of the time-independent Schrodinger equation. So these are not exactly wave function solutions. Wave functions require that I multiply them with the time-dependent part, but it's not going to play much role in terms of the conclusions that I'm going to draw, so it doesn't really make much of a difference. If you're interested to write the complete wave function solution, you can write exponential to the power iota omega t, minus iota omega t as an additional multiplicative term. It's not going to make any difference to our conclusions. So let's apply x is equal to 0 here. So if x is equal to 0, this becomes a e to the power 0 plus b e to the power 0 is equal to c e to the power 0, which means that a plus b is equal to c. All right. And the second, let's suppose this is point number 1. And the second boundary condition I want to impose is that the derivative of psi1 at x is equal to 0 and the derivative of psi2 at x is equal to 0 are also both equal. All right. Which means that if I take the derivative of psi1, it should come out to be iota k1 a, and then at x is equal to 0 e to the power 0 minus iota k1 b and e to the power 0 is equal to, here I have minus k2 c e to the power 0, which means that this expression becomes iota k1 a minus b is equal to, here we have minus k2 c, or I have a minus b is equal to k2 upon k1 iota, so minus iota will become in the denominator will become plus iota in the numerator, and this is C. So let's suppose this is point number 2. So if I add point number 1 and 2, just add them. If I add them, I should get A plus B, A minus B, B and B gets cancelled. I have 2A is equal to, C is a common, 1 plus iota K2 upon K1. Okay, so this becomes C K1 plus iota K2 upon K1, which finally means that C in terms of A is equal to what? So C in terms of A is equal to 2 K1 upon K1 plus iota K2 A. That's it. So if I apply this term here in this expression, so this expression becomes, the probability is equal to, therefore, so 2 and 2 we have 4, K1 square, and then we have mod square of K1 plus iota K2. So you have K1 plus K2 into K1 minus K2, which becomes, sorry, K1 plus iota K2 into K1 minus iota K2, which becomes K1 square minus iota K2 square, iota K2 whole square, which is plus K2 square, right? And you have A mod square e to the power minus 2K2x. So as the particle penetrates deep in the barrier, its probability of being found decreases exponentially. These values we can determine from the ratio of the energy of the particle and the barrier. So K1 is 2m e upon h cross square root over, K2 is 2m v0 minus e upon h cross square root over, right? And A is simply the amplitude of the incident wave. So if we are familiar with the problem, the amplitude of the incident wave basically gives us an idea about what A is. So this is the very important probability density of the particle inside a constant barrier whose energy is greater than the particle's energy but extends to infinity. Now there is one more thing I want to mention before I wrap up this particular topic, is that even though the particle penetrates inside the barrier, it eventually comes back. Why? Because of the way I have taken this construction. This constant potential extends up to x is equal to infinity, right? So the particle cannot keep going up to infinity. It will become 0. So eventually, even though the particle does penetrate through, will go back. And I can show it to you by calculating the reflection coefficient. Okay, if I want to calculate the reflection coefficient, what is C here? If I plug C back into this particular equation, so this becomes A plus B is equal to C. C is equal to 2K1 upon K1 plus iota K2 A. So therefore, from here I can figure out what B is. B is equal to, so B is equal to 2K1 minus K1 minus iota K2 divided by K1 plus iota K2 A. So this B becomes K1 minus iota K2 K1 divided by K1 plus iota K2. This is the ratio of the constants B and A. Now, if I want to calculate the reflection coefficient, so what is the probability that the wave that strikes this barrier will be reflected back? That reflection coefficient, if I want to calculate, so all these lines are separate, okay? So if I want to calculate the reflection coefficient comes out to be R is equal to the probability current density of the reflected wave upon the probability current density of the incident wave, which comes out to be B upon A mod square. So this is the ratio of the coefficients of B and A, which are the constants associated with the reflected wave and the incident wave. If you are interested in how I came up with this expression, I have solved this in my previous video where I discussed the same problem for E greater than V0. There also we had reflected wave. So there I have derived this formula using the concept of probability current density. If you want, you can check that out. Otherwise, the reflection coefficient quite simply is nothing but the coefficient, the constant associated with the reflected wave or the amplitude associated with the reflected wave upon the amplitude associated with the incident wave mod square. If I do that, B upon A, this comes out to be K minus iota K2 upon K1 plus iota K2 mod square. Because this mod square, I will have K1 minus iota K2 times K1 plus iota K2, which will come out to be K1 square plus K2 square. Similarly, K1 plus iota K2 in the denominator times K1 minus iota K2, which will always also come out to be K1 square plus K2 square, because it's a mod, right? So this gets cancelled, is equal to 1. So the reflection coefficient is equal to 1, just like classical mechanics. That means eventually the particle will go back, because a particle cannot keep on moving forward up to infinity because the potential extends up to infinity. Now the situation is very different if we had a finite barrier. If instead of this potential extending to infinity, if I had a finite barrier, then the situation will be very different. And I'm going to discuss that situation in the next video where I talk about quantum tunneling. However, this is just part of that concept. Because the potential extends up to infinity, the particle cannot keep on going up to infinity. It will eventually come back. And because if I bombard 100 particles, no matter how much deep it penetrates, it will eventually go back. Therefore, the reflection coefficient is equal to 1, just like in classical physics. However, unlike classical physics, in quantum mechanics, particle does have a probability of being found inside a barrier, even though it doesn't have sufficient energy to penetrate that particular barrier. So if I have to draw a simple graph to show you what's happening, for x is equal to 0 going to infinity, and here we have the probability density, which is psi 2 x mod square. All right, it simply goes exponentially down like this. That's all. This is the interesting case of the step potential, where a particle is approaching from the left, has energy less than the barrier height itself. In the next video, we are going to discuss something very interesting. What if I make this barrier of finite width? If instead of the barrier extending up to infinity, if it had finite width, then the particle would just plop on the next side, on the other region, which has a very interesting ramifications in the context of quantum mechanics, in the context of technology, which I'm going to discuss in the next video. That is all for today. Thank you so much. Take care. Bye-bye.